Good evening, everyone. Now, this is the first lecture for CS1, that is our core statistics ones. This is a demo lecture. So, okay. First of all, we'll talk about the basics of what we cover in CS1. At any time, if you have any question, you can either type or unmute yourself and ask. Okay. So, don't hesitate. Just ask me any question you might have. So core statistics 1, that contains statistics. So we say from basic statistic to advanced, that is analytical statistic. This is covered in CS1. Okay. When it comes to CS2, you have much more advanced statistics, that is called as modeling. Okay, so that is CS2. You will study that later. Now, when we talk about our basic and analytical statistics, we'll be starting from very basic. So we'll be covering some basic chapters as well. That is not part of our course. So I say we have B1, B2, B3. We have data summary, probability, and random variables. These are the basic topics that we'll be covering. That is not part of our course. And after that comes the topics that are part of our course. So we have 15 chapters here. So at the beginning we'll be talking about basics. So first, let's say 6 chapters are the basics, and from chapter 7 to chapter 15, these are the analytical part. So this is how we are going to cover our course. Okay, so we'll be studying the basic chapters. We have 3 that are not part of our course, and after that we have 6 that are part of our course, and then we are going to these 7, or from 7 to 15, these are also the analytical chapters. Now other than this, so this is the course of part A. So whenever we are talking about a CS1 examination, we have examination in 2 parts. So part A would be online written, 100 marks, and then part B is online R programming, that is also 100 marks. Now R programming is a statistical language that we use to apply all the analysis that we are going to study here. So everything that we are going to study in part A, we are going to understand how would we apply it in part B, that is using R programming. So there is a software called R Studio that we use to run this R programming. When we come up to that, we'll talk about it. Okay. Now, when it comes to examination, you have to give both of those examination. What they do is they take part A multiplied by 0.7, then add part B into 0.3. This is your total marks. Okay, this is total marks. So they are giving more weightage to part A, that is your written examination, and less weightage to part B, that is your what do we say, R programming. Okay, and usually for IFOA, the passing mark is about 60. It depends. It might be less than 60, it might be more than 60, but usually it is 60. Okay. Passing marks. It's variable. Okay, so it may vary. It's not always fixed. Now, when it comes to IAI, if you are giving examination from Indian Institute, IAI, the passing marks is 50. Fixed. It will always be 50. So we have two institutes. We have IFOA, that is the UK institute, and IAI, that is the Indian institute. Now both of them have the course exactly same. So this chapters that we are going to study is going to be exactly same. The paper pattern is very similar. So the questions that you see are almost the same. So the difference is, and both the examinations are online. Okay, so both IAI as well as IFOA, you have to give the examination from your home itself. Just there is small difference. Usually we say that IAI paper is slightly more difficult and their passing mark is less. IFOA comparatively it's easier and its passing mark goes around 60. So IFOA has a variable passing mark. It might be 52, it might be 54, 56, 58, 60. It has been 62 as well. So depending on whether they feel that the examination is going to be, the level of the examination, they keep the passing mark. Okay. So Apurva, you're asking which institute to choose if planning to get a job abroad. If you're planning to get a job abroad, definitely choose IFOA. IFOA, you can get job anywhere in the world. IAI, you will get around India. Most of the countries will recognize it, but IFOA, you will definitely get anywhere in the world. Plus what happens is, let's say during your graduation, you may not be able to complete all the 13 papers. It's not possible. So if you choose for IAI, giving examination might be a little bit of problematic from outside India. But now it is online. This is the first time it will be online, so actually you can give anywhere from the world. Otherwise you had to come to India to give the examination. IFOA anyways, it is online and you can give examination from anywhere in the world. So that will not be a problem for both the institutes, but as I said, recognition wise, IFOA is much more recognized all over the world. Okay, so see, when it comes to companies in India, they won't differentiate between the institutes. So they would ask whether you have cleared a paper or not. So basically you have CM1, CS1, CM2, CS2, CB1, CB2. These are the 6 papers that are our basic beginning papers, right? So depending on the company, they may ask, like life insurance will say whether you have cleared CM1 and CS1 or not. So these are the 2 papers that are important for a life insurance company. When it comes to general insurance company, they will ask you whether you have cleared these 3 papers or not. When it comes to investment company, they will ask you whether you have completed these 3 papers or not. Okay. These CB1 and CB2 are more of a filler papers. Usually what they say is you should have completed 4 papers, including CM1 and CS1. Okay, so in this case, the other 2 papers, whether it is CM2 or CS2 or whether it is CB1 or CB2, it does not matter. So there's no company who actually requires that you should clear CB1 or CB2. They are just filler papers. Okay, so CB1 is about accountings and finance, and CB2 is economics. Okay, so these are basics that you should know, but there's no requirement directly in any of the field that we work in. Okay, so for any institute, especially in India, they do not care whether you have cleared those papers from IFOA or whether you have cleared those paper from IAI. Okay, but when it comes to companies abroad, like in UK, Germany, these kind of countries, they would always prefer institute should be IFOA. Okay, but if you go to Dubai, if you go to Australia, if you go to South Africa, they will also accept IAI. That will also be okay. Okay, Harshit, you are asking for freelancing or remote based jobs, which institute help pays better salary and more see, again, it will not depend on whether you have cleared from IFOA or IAI. It will depend where are you actually working. In India, the salary would be comparatively less. UK salary will be almost 10 times more than what you would get in India. Okay, so it's more about the company and the place that you are working rather than which institute, because as I said, internationally also they both are equally recognized. Okay, now freelancing, if you want to work as an actuary as a freelancer, you should have at least 15 years of experience. Okay, only then somebody will actually be hiring you as a freelancer. And you don't call it as a freelancer, you call it as a what do we say, consulting actually. Okay, you will never call them as freelancer. Okay, so Isha, you're asking, can you please repeat what paper should we clear for investment? For investment, CM2 is the important one. For CM2, you should be clearing these three. So CM1, CS1 and CM2. Okay, these are the three papers that are important for investment. Okay, so you will learn investment in CM2. Okay, this is the paper, but of course you will require the knowledge of CM1 and CS1 to understand CM2. Okay. Okay, so institute will not matter much, but it's easier to clear papers from IFOA. Okay, IAI has been making more strides, better strides to make their paper pattern and stuff consistent. I think within a year or so they would make big changes so that they won't have to deal with there have been complaints of whether the portion what do we say, the questions have been out of the course and stuff. That has happened before, but they are becoming better when it comes to designing question paper and what do we say, correcting question papers. IFOA usually don't have such problems, so that is why we usually recommend IFOA. Okay, so let's start with our CS1 course. We are going to start with the basic chapter 2, that is probability. At any time, if you feel like, you can unmute yourself and ask question as well. Okay, that's not a problem. Now to learn probability, first we'll talk about sets. Now we study sets during our school. I think yes, you can Rehman, you can unmute yourself and ask.
Thank you, sir. Basically, sir, I am from Bangladesh.
Yes.
I am just attending your class, or I'll get enrolled to just reinforce my knowledge in statistics.
Okay.
By training, I am an engineer, but during my time, there was no statistics book. So what is the regular time of this class?
See, regular timing. So according to Indian Standard Time, I'll be talking about Indian Standard Time. Okay. So these are the timings. So for CS1, we'll have Saturday 4 to 6 p.m. Okay, and Sunday from it will be 9 to 11 and sometimes 11 to till 1 o'clock. So because when we are taking R programming, we may require extra classes. So that is why here it is at 9 to 1.
But in CS1 there will be no R programming, right?
CS1 there is R programming.
Okay. So in this course you will also teach the R programming?
Yes, I will be teaching the R programming as well.
Okay, so from Saturday from 4 to 6?
Yes, 4 to 6.
Sunday, 9 to 11?
Yes. Okay.
Thank you.
So
it will be better for me. Thank
the fees for online and offline batch is 23,000, and recorded lectures are also available. And okay, I'll talk about this also. There is a 10% discount if you pay the full fees by 15th April. Okay. Actually 15th April has already gone. So I think there is more discount and stuff. It will be available by the end of this week as well. Okay, that is next week. Most likely this is not the correct date. You can contact the office to clear exact date.
Okay, thank you.
Yeah. Chalo. So let's talk about sets. Now I hope everybody has studied sets. If you have not studied sets, let me know beforehand. Okay, I'll go into more depth. So yes, Rahman.
Sir, I have not studied set too much.
Okay. So I'll go into a little bit of depth. Okay, Rashid is saying I am also from Bangladesh. We don't have weekend on Sunday, and I have university classes during that time slot. Will there be see every class, every online class we do record, and it will be present for you to refer later. So if you are not able to attend the class, no problem, within an hour or so we upload that class. Okay, so don't worry about it. So sets. Now set is nothing but a collection of similar items. So when I say a set, I represent a set always with a capital letter, and we write its item in the curly brackets. So let's say I have A, B, C and D. So this will be a set. We'll say this is the set of first 4 letters in English language. Okay, you can say it is lowercase letters, we can have uppercase letters, and so many everything. Okay, so there are some rules in which sets are governed. So let's say I have this B, another set that has C, D, E and F. Okay, so these are 2 sets. Now you will see that there are 2 letters that are common in this set, C and D. Now we always say anything in a set, any item in a set can occur only once. That means this C is exactly same as this C. There is only one C. Okay, that is what we assume. Any item, any value occurs only once in a set. Okay, so C and D, both of them are exactly same. These are 2 elements that are common to each other. Now when it comes to representing it visually, we draw something called as a Venn diagram. Okay, so Venn diagram, in that we will be representing sets with circles, usually what we call areas. Okay, so here I will say this is A and this is B. The elements, I would say A and B are here, and C and D are here, E and F. This is how we'll represent them. Okay, so you can see C and D occurs only once, but they are common to both the sets A and B. Okay, so this is how we represent a set, and this big box, blue box, is called as a universal set, usually represented by X or a U or a S. These are the terms that we usually use for a universal set. A universal set contains everything that is possible in the universe, we will say, is contained in the universal set. Okay, so usually whenever we are dealing with a problem, so let's say this is a problem where I have 2 sets and I have 6 letters. So I will say all of those 6 letters will be inside the universal set X. Okay, now there are a few things that we usually talk about. We'll say number of elements. I'll write it as NA. This is nothing but number of elements in A. In this case, I'll say NA, number of elements is 4. I have 4 elements here. Okay. Then number of elements in B, that is again 4. So we usually talk about the number of elements. In this case, number of elements in universal set. Number of elements in universal set are 6. There are total 6 elements in this case. Let's say I also had G and H. Let's say G and H that were not part of A or B. So here I would have 8 elements, okay, in universal set, whereas 4 of them are in A and 4 of them are in B. Okay. Then we say something called as a union. Okay, I'll say A union B. This is called as a union. Okay. Union means and. Okay. Rather, when we are actually talking about statements, mathematical statements can be directly translated into English statements. So if I am talking about a element that is present in the union, so let's say this A, I'll say A is present in union of A and B. So how would I say? I'll say A is present in A element, set A or set B. So in English language, union represents or. Okay. So this set will be any element that is in A or in B will be part of A union B. Okay, any element that is part of A or B. So A had A, B, C, D and B had C, D, E, F. Okay. And as I said, C and D occurs only once. They are just common elements. That is why we'll write it only once. Okay. In a union, we'll always write it only once. Similarly, we have A intersection B. This is called as intersection. Or we'll use the word and. Because we'll say any element that is in A and in B will be part of the intersection A and B. Okay. So here only the elements that are in A and in B both. So there are only 2 elements that are in A and in B both. That is C and D. Similarly, if I want the number of elements in A union B, you can count it. I have 6. Number of elements in A intersection B, we have 2. Using this, we can make a formula. We can say number of elements in A union B will be equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. You can use the diagram to prove it, or you can just use the numbers. Here, using diagram, you will say everything that is part of A plus everything that is part of B. When I add them, this intersection will be added 2 times. So I have to subtract it once. So the formula we'll make is A union B is number of elements in A plus number of elements in B minus number of elements in A intersection B. Is that clear? Now we can use another term. There is something called as complement. Complement of any set, let's say complement of A, we will represent it as A dash, or sometimes AC, or A bar. These are usually the different types of terms that are used to represent a complement. A complement means everything other than. It means everything other than. So what we mean here is this represents everything other than A. Okay. So a complement can be written as universal set minus the element. A complement would be nothing but universal set minus the set. So number of elements in a complement would be nothing but number of elements in universal set minus number of elements in A. Now when it comes to representing, if I say A complement, everything other than A would represent A complement. So the shaded region, the region that I am shading, you can see it is everything other than A. I am leaving A, B, C and D, and everything else I have shaded, that would represent A complement. Okay. So everything that is not part of A would come into A complement. Now we can use that A complement or the complements to represent A union B as well. Let's show you the Venn diagram. So this is the Venn diagram. Now if I want to represent this area I will call it as only A. Only A. So I'll say number of elements in only A plus this area I'll call it as only B. Number of elements in only B, and then plus the middle region is just A intersection B. It is just the intersection, right? So if I want to write only A in the mathematical terms, in these terms that we have studied, can anybody tell me how would I write only A, the region only A, using unions and intersections? Okay, this unions, intersection and complement. Anyone? So if I am talking about only A, okay, this region I would say it contains A, anything that is in A but not in B. Okay, so it represents A, but when I say but is similar to an and. Okay, that is complement. Not in B, that would be B complement. So number of elements in A but not B would come into only A. Similarly for B, I'll say the element is in not A and B. So any element that is not in A but is in B would come into only B. And then A intersection B as it is. Right? So this is another way of writing A union B using complements. So now we have talked about two formulas. Now here we had considered only two sets. Okay, I'll repeat this when I'm talking about only A. Now, okay, I talked about logically. Now let's talk about mathematically. When I say A intersection B complement, when I say A intersection B complement, what area does it represent? So I will represent A with red. I will shade out red. A, this is A. And for B complement, I will use blue. B complement is everything other than B. So I will shade everything other than B. It should contain everything but B. So everything other than B. Now you can see what is common between them. The common intersection means whatever is common between them. So what is common? You can see this only A part, that is this part. Okay. So when I say A intersection not B or complement B, that means I am talking about the region only A. It contains elements that are only in A and not in B. Okay. Similarly, only B region will be A complement and B. And the third is the intersection, that's the middle part. Now what if we have three sets? Let's say I have three sets. This is my A. Let's say I have A, B and C. C is going out of universal set. Okay, I have three sets A, B and C. Now what if I want to find number of elements in A union B union C? Okay. Now the easiest way, or the formula that you might have learned before, is just number of elements in A, B and C. We will add them up. Okay. Now when I'm adding them up, if you see the common region, this is A intersection B, that has been added twice. This is B intersection C, that has been added twice. And this is A intersection C, that has been added twice. So if they have been added two times, I have to subtract them once. So I will subtract number of elements in A intersection B, number of elements in B intersection C, number of elements in A intersection C. Okay. Now when we subtracted this intersection part, all three of them contained this portion. Okay. So it was contained in A, B and C, so we added it three times. It was contained in intersections, so we subtracted it three times. So this triple intersection, this intersection that is three times, has not been included anywhere. So I will add them. Triple intersection, just add them. Okay. A intersection B intersection C. This is just a general formula. Okay, this is just a general formula. I'll talk about the general formula in a minute. But we can represent this by adding up all the different sections as well. I can add up this section, this section. I will call it as only A. Okay. I will represent it with small a. This I will represent with small b. This I will represent with small c. This is A, B, C represents only A, only B, only C. Let's say this is D, E and F. D represents A and B but not C. E represents B and C but not A. F represents A and C but not B. And this G represents all three together. Okay, or intersection between all three. So my A union B union C can also be written as the small a plus B plus C D E F and G. I can add up these individual regions to make A union B union C. Now how do we represent this only A part? When I'm talking about only A, that only A represents the region that is part of A but not of C but not of B. So I can say this is number of elements in A but not in B but not in C. This is how we will represent only A. It is part of A but not part of B but not part of C. Similarly, only B, not A but B, not C. Only C, not A but not B but C. Now if we talk about this D region, this part is common to A and B but not C, right? It is part of A and B but it is not part of C. So I'll say it is A and B but not C. It is part of A and B but not C. Similarly, I'll have not A but B and C, and A and but not B and C. And lastly, triple intersection, A intersection B intersection C. These are the different ways we write the formula using complement and without using complement. I'll tell you a few more simple formulas. We say if I have intersection, let's say A union B complement. If I have a complement of a union, it just becomes A complement intersection B complement. Similarly, if I have A intersection B, the whole complement, that is same as A complement union B complement. Okay. So these are very basics, and I'm going into basics because we use the concepts of sets to make the formulas of probability. Okay, so we are not actually going to study sets, we are going to study probability. Now probability is very similar to a set. When I said I have a set A that contains certain elements. Now when it comes to probability, we are going to say we have an event A. We have an event A that has certain outcomes. So we'll say A, B, C and D are nothing but outcomes. Okay. So here A will now become events. And these will become outcomes. So we say what is the probability of an event A? PA means probability of an event A. That is nothing but number of elements or number of outcomes in the event A upon number of outcomes in the universal set or the total outcomes. This would be, we'll call it as desired outcomes. These are the desired outcomes upon total outcomes. Probability is nothing but desired outcomes upon total outcomes. That means we'll say these were the possible outcomes that will give us success upon total outcomes, that means success and failure both. That gives us probability of event A. Now if I ask you what is probability, can you tell me what do you think when I say probability? What comes into your mind? First thing, what is probability? You can unmute yourself and answer, or you can type. Okay. So I've got an answer chance. I've got an answer likelihood. Chance or something happening. Yes, perfect. Both are correct answer. All three of you have given the correct answer. When I say chance of something happening, or likelihood, how likely is something to happen, both actually means nothing but probability. You may also say odds. You may also heard the word odds. What are the odds? Now odds are slightly different from chance. Okay, so if I say that the odds are 3:1, okay, if the odds are 3:1, that means chances are 3/4, or the probability is 3/4. Okay, so odds just represents all the possible chances. Okay, out of 4, 3 times I will get success and 1 times I will get failure. And when we convert it into probability, it becomes 3/4. So chance and likelihood and probability, all three of these terms means the same. These are the 3 terms that I myself will always use interchangeably. Okay, if I use the word likelihood, the word likelihood just means probability. So this is how we calculate probability, the desired outcomes upon total outcome. This is the probability formula. Now when it comes to sets, we said number of elements in. Yes, Rahman?
Sir, probability of A has got 4 outcomes, right?
Yes.
So if I pick, I'll get only either A or B or C or D. But I'll get one outcome, right?
Yes. So see, I'm saying if you get A, B, C or D, it is success.
Okay.
But if you get, see, in universal we had E, F, G, H also. Right, in this example I had E, F, G, H. Right. So in this case I would say that if you get A, B, C or D, it is success, but if you get E, F, G, H, it is failure. So my X, that is universal set, would be all of them. So here probability would be 4 out of 8, that is 1/2. Okay. So this is our formula. We can directly convert this into probability. I can divide both sides by nx. If I divide both sides by nx, what would happen is I'll get probability of A union B, probability of A plus probability of B minus probability of A intersection B. So every formula of set directly converts into formula of probability. That means every formula of set that is of number of elements will directly convert. Yes.
If I get, like, suppose A, the small a, 3 times. So how can I represent the set
A? Here you are saying A comes out to be 3 times. That is what you are saying?
The small a.
Small a, yeah. So when it comes to set, just as I said, that one element can only occur once in a set. Okay. So there is only one A.
Probability.
Yeah. So either you can say, see, if you have something like you have 3, hearts and 1 diamond. Right? How do you represent that? So you will say this is 1 heart, this is 2nd heart, this is 3rd heart, and this is a diamond.
No, I cannot see the diagram.
No, I did not draw a diagram. I was just saying A will represent the 1st heart, B will represent the 2nd heart, C will represent the 3rd heart, and D will represent the diamond. I'm just saying there are 3 hearts. They are represented by A, B, and C. And there is a diamond that is represented by D. Okay. So because I would not say that there are 3 A's. I will not say A, and A. This is against set. Okay. These are against the rules of sets. Okay. Now see, I can draw something like this. I can say I tossed a coin 5 times. If I tossed a coin 5 times, the set of my answer, let's say, is heads, heads, tails, heads, tails. Let's say this is how I got my answer. This is also a set. You might say that I have got H 3 times and I have got tails 2 times. They are repeating. But I would say this is the outcome of the first coin. Okay, so this is basically I would represent this as A, B, C, D, and E. These are totally different answers. Okay. They mean the same, but when I'm representing them in sets, they are different outcomes. This is outcome of first coin. This is outcome of second coin. This is outcome of third coin. Outcome of fourth coin. And outcome of fifth coin. Okay. Let's get back to the probability formula. So every formula can be converted into probability. So here, like this formula, all I have to do is, instead of n, write p. Similarly here, all I have to do is, instead of n, write p. So instead of n, I have to write p. That becomes the probabilities that becomes the formulas that we'll use for probability. Okay. So every formula of set can be converted into a formula of probability. That is why we talked about sets here. Let me give you an example. So we are talking about a deck of 52 cards. Okay, randomly selecting a card, and we are saying the event A represents the card is a 7. Event B represents card is a club. Okay. So now I want to find the probability that the card is, first of all, A, second, B, third, A union B, okay, instead of writing this, I'll just say first part. Find the probability that the card is a 7. Second, the card is a club. Third, card is a 7 or a club. Actually, first let's say 7 and a club. Fourth is a 7 or a club. So it's a random deck of 52 cards. How many 7s are there? 4. So we'll say probability of A, that means the card is a 7, is going to be 4 out of 52. There are 4 correct answers, 4 desired outcomes out of 52 total outcomes, right? Similarly, for the second part, how many clubs? There will be 13 clubs out of 52, right? Will not simplify it. You can definitely simplify it to 1 by 13 and 1 by 4. For now, I am not simplifying it. Third, when I say it is a 7 and a club, we are talking about intersection. So I'll say probability A intersection B. Now, how many cards do we have which is 7 and a club?
1.
Only one card. Yes, perfect. Only one card that is 7 and a club. So 1 by 52. Right. And how many cards are 7 or a club? 16. Perfect. So we have 4 7s and we have 13 clubs, but one of them is 7 of club, so that is common. So you can say 3 and 13, I'll get 16. So I have 16 by 52. And you can also find that with this formula. You can say probability of A union B will be equal to probability of A plus probability of B minus probability of A intersection B. You can do that. This is the reason I did not simplify it, because I wanted to keep the denominator same. Right. Simple. So this is how we use the theory of sets to make the formulas of probability. Now let's talk about mutually exclusive events. Now, what are mutually exclusive events? We say You say when two events do not have any outcomes in common, they'll be called as mutually exclusive events. Okay. So they do not have anything in common. That means their intersection is 0. So we'll say probability A intersection B is 0. There's nothing in common. So for example, I'll say red cards and black cards. So there is no card that is red as well as black. Correct. So that is why there is nothing in common. They are mutually exclusive events. Okay. So if any two events do not have any outcomes in common, they are called as mutually exclusive, and mathematically we'll say their intersection is 0. Then we have mutually exhaustive events. Mutually exhaustive. So two events that together contains every outcome would be called as mutually exhaustive. That means together they exhaust all possibilities. So together they are exhausting all possibilities. That means they are mutually exhaustive. When I say they are what do we say? They are mutually exhaustive. That means A union B will be equal to a universal set. Okay. It will exhaust every possible outcome. Okay. So probability of A union B will be equal to 1. It will be number of elements in universal set upon number of elements in universal set. That is 1. So this becomes mutually exhaustive events. They are exhausting everything. Okay. Now, I would say another example is red cards and black cards. Right. Here example I'll give again. Red cards and black cards. So in a deck of 52 cards, 36 are red and 36 are black. There is nothing in common, and together they will make up the whole 52 cards. So they are mutually exclusive as well as mutually exhaustive events. Any problem here?
Why? What is the reason of introducing this term exhaustive event?
See, we use that later on. So the term exhaustive just gives us an idea that all the possible outcomes have been covered. Okay, later on we'll be using it. Okay. We have exhausted all the possible outcomes. We use the word exhausted to say that everything is spent, right? Now, independent events. This is very important. So we say when the occurrence or non-occurrence of an event does not affect the occurrence or non-occurrence of another event, then they are independent events. Okay. Something happening or not happening is not affecting something happening or not happening, then those two events must be independent of each other. Okay. Now if I say I ate a mango and there was rainfall, are those two events independent or whether they are dependent? How do I recognize that? I will eat another mango, and if there is rainfall again, I will say maybe they are connected to each other. And when I do not eat mango, there is no rainfall. If that happens, then they are not independent. That means my eating mango is affecting the rainfall. But there will be times when I am not eating mango and still there is rainfall, and there will be times when I eat mango but there will be no rainfall. So occurrence or non-occurrence, that means my eating mango or not eating mango is not affecting whether there will be rainfall or there will not be rainfall. Occurrence or non-occurrence of rainfall. In such case, I will say my eating mango and rainfall are independent of each other. Right? That makes sense? My occurrence or non-occurrence of one event, if it affects or does not affect the occurrence or non-occurrence of the second event, then they would be called as independent events. Okay. Mathematically, this is how we represent it. We'll say A intersection B. That means A and B occurring together. When I say A intersection B, I am saying A and B occurring together. Probability of that is probability of A occurring and probability of B occurring. That means they two occurring independently and they two occurring together. There's no difference between them. That means A did not affect B, B did not affect A. I can also say A occurring but B not occurring. B complement means B not occurring. So A occurring and B not occurring are also independent of each other, because whether A occurs or not, that is not affecting whether B will occur or not. So I can use all such combinations. So occurrence of A is not affecting occurrence of B. Occurrence of A is not affecting non-occurrence of B. Non-occurrence of A not affecting occurrence of B, and non-occurrence of A not affecting non-occurrence of B. Is this question in product format? Yes, product means multiplication, so these are multiplications. Okay. P is just the representation of probability. P is the word for probability.
Sir,
yes.
The first one, the probability of A intersection B equal to probability of A into probability of B. So you mean A and B occurring together but independently?
Yes. So see, probability of A and B occurring together. What is the probability of that? I will say probability of A occurring independently and probability of B occurring independently. These two events happening together is same as probability of A and B occurring together. Okay.
So can we compare this with the set theory part?
Yes. So everything can be compared into set theory. Okay. So you can prove all of these. Okay. But how to prove whether probabilities will be equal or not, this we'll learn later. Okay. This we will cover in chapter 3. So don't worry too much right now. We will use distributions and stuff to prove these things. So right now you will take it as a rule. Okay. So if we have two independent events, then both of them occurring together is same as independently occurring and their probability is getting multiplied. Okay. Now if I say, okay, example, pick one card. Okay. And again, A is 7, B is club. Can you tell me whether these are independent or not?
Not independent.
They are not independent. Anybody else? I've got two answers is not independent. Anybody else? Now what if I take this rule? If I say probability of A, it was 4 by 52. Probability of B was 13 by 52. Probability of A intersection B was 1 by 52. If I multiply these two, I will actually get 1 by 52. Okay, numerator will be 52 and I'll get 1 by 52. Now, would we say they are independent?
No.
Why not?
Because I can get the black 7, club 7, okay, together.
So that is what the probability of 1 by 52 is. See, when I'm saying independent, that does not mean both of them cannot occur together. They can occur. This club and a 7 can occur together. That is a 7 of clubs, right? That is possible. That does not tell us. So there should be an intersection. Without an intersection, we cannot have independence. I'll tell you, this is neither independent nor dependent. I tricked you. Now the tricky part was here. We picked only one card. This is just one event. This A being 7 and B being a club. These are outcomes of a single event. And the event was picking one card. Now how can one single event be independent to itself? It's not possible, right? So I should be picking two cards. So this is neither independent nor dependent. Yes, Rashid.
So for independent events, probability of one event happening will have nothing in common with another event happening. But there is a common option, right?
Yes, but when you are saying one event happening and another event happening, there are two events there, right? When I'm saying pick one card, that just means I am talking about single event. Now single event cannot be dependent or independent on itself, right? These are A and B are nothing but outcomes of a single event. Okay. If I want to see whether picking a 7 and picking a club are dependent or independent, I need two cards. I'll now say pick two cards. Okay. and in the first card I get a 7. Second card I get a club. Now I ask you, this is A and this is B. Now I ask you whether A and B are independent or dependent. Now can you tell me?
Probably dependent. At least not independent.
Again, I tricked you here because it depends on how we are picking these two cards. Okay. Now there is something called as replacement. There are two ways we can pick this card, whether we replace the first card or whether we do not replace the first card. What does that mean? That means, let's see, I picked randomly a first card and then I saw what that card is and I put that back in the deck, reshuffle it. That is will be called as replaced, and then I pick the second card. If that happens, that means I have replaced it. Okay. If I do not replace, what would happen? See, when I pick the first card, irrespective of what that is, I don't know what that is now, I pick another card. Okay. Now when I'm picking the second card, I already have the first card in my hand. I did not replace it back, and I picked the second card now. In the deck, I had only 51 cards, right? Because I had one card in my hand. So whether it is club, whether it is 7, in the deck there are only 51 cards. So for the second card, my denominator is 51. And whether my first card was a club or not will affect whether my second card, what is the probability of my second card being club? Because there are only 13 clubs in the deck. If my first card was a club, then in the deck there will be only 12 clubs left. But if my first card was not a club, then I will have total 13 cards that are going to be clubs in the deck. So you can see how the outcome of the first card is affecting the outcome of the second card. Right? If the outcome of the first card is affecting the outcome of the second card, then they are not independent. So when I say we are not replacing them, then it becomes not independent. We never say the word dependent, although it means dependent, but we say mathematically I cannot prove dependency, I can only prove independence. Okay, I can only prove independence, I cannot prove dependency. And if I am able to replace, then they are independent. I'll give you an example of that as well. That if we replace the first card, let's say irrespective of what my first card was, I'll say probability that I will get a 7 for the first card. Okay, probability of A is 4 by 52 and probability of B is 13 by 52, irrespective of whether the first card was a 7 or not, whether it was club or not, whether it was something else. It does not matter because I replaced my first card back into the deck. It does not matter whether it was a club, whether it was not a club. Right? So they are independent. If we do not replace, then they are not independent. We get very simple questions on this. Okay, I'll just make a question. So they're saying 4 cards are randomly chosen from a deck of 52 cards. Find the probability that all 4 are ace. Ace means A, right? All 4 are ace. First is if all cards are replaced after selection. That means we have replacement. If we have replacement, then they are independent, right? We said if we have replacement, then they are independent. Okay. So I'll say probability of A is 4 by 52. That is 1 by 13. Because I have 4 aces in a deck of 52 cards. And because there is replacement, they are all independent. We have independent events.
Sir, could you please just explain it again? If we replace them, why it is independent?
Because we are see, let's say my first card was a ace. Okay, if my first card was a ace, in the deck you will say there are 3 more aces now, and total number of cards that are there in the deck now are 51. But if I replace it back inside the deck, now I have 52 cards and 4 aces, right? 4 by 52. Now let's say what if in the first card I get not a ace. I am not getting an ace. So in the deck I have 4 aces and 51 cards. But when I replace it back in the deck, I have now 4 aces out of 52 cards. So every time when I replace the card back in the deck, my probability of selecting an ace again becomes the same as what it was previously. Right? It will always be 4 by 52 irrespective of what number or what I got in the deck, in the selection, first selection, second selection and so on. The probability will remain same because I have 4 aces by 52 aces, 52 cards before every selection. Okay. So because they are independent, probability that I will get an ace and another ace and another ace and another ace is just probability of A raised to 4 multiplied with each other 4 times. Okay, 1 by 13 raised to 4. Okay. Now tomorrow, I'll leave it right now here. Tomorrow we'll talk about what kind of calculators we are going to use. We are going to use scientific calculators and we'll complete this question tomorrow. But I would like you to try and figure out how will we solve this question when there is no replacement. What happens if there is no replacement? Okay. So tomorrow our lecture is going to be in the morning. What's the timing? Sunday. We have 9 to 10:30. Okay. So tomorrow, if you have any doubts about our classes or actual science, you can ask me that too. Okay. So we will connect again at 9 a.m. with the same link that you used today. Okay.
Sir, would you please suggest a name of any book so that we can practice?
See, we will give you the book. Don't worry. Okay. Tomorrow I'll discuss about the book as well. Okay. So I'll give you the book as well. But right now, just study what we did today. Okay, because this is a basic chapter. I'll give you a book for the basic chapter as well, and I'll give you the book for the actual portion as well. Okay, sure. Let's end the class here. Okay, we'll meet tomorrow. Bye.